Well, thank you for coming, everyone. I appreciate you being here. I know we have an exam tomorrow, and the material we'll cover today will not be on the exam, but I appreciate you being here. I think that the topic today, which is improving Rankine cycle efficiency, is at least in some way a review of the Rankine cycle portion of the material we've covered so far. So it's certainly still relevant to the work that you'll be asked to do on the exam tomorrow. So this is, I guess, starting here, we have an announcement or a reminder that the exam is tomorrow, that it will run from 3 p.m. to 7 p.m. Eastern Standard Time. We'll access material in the same way that we did in the last exam, where the multiple choice questions will be available via quiz on my courses, and the long answer problems will be available via assignment drop boxes. So when you go to the assignment drop box, you will be able to see the question. So there'll be a PDF loaded to the assignment Dropbox. There is also material in the, I think it's under online exam materials, where you'll be able to see the equation sheet. So does anyone have questions about the exam or how to access the content? All right, if not, we will move forward. So we've been talking about thermodynamics, right? And literally what thermodynamics means is that we're turning energy in the form of heat to energy in the form of dynamic force or kinetic energy or some sort of mechanical work. So really what we're trying to do in thermodynamics is put heat in and get work. At least that's kind of the original concept of mechanical engineer's view of thermodynamics, right? And we talked about how, this thermodynamic study, in part sort of came out of this idea of steam engines, where this is literally what we were trying to do, was burn coal to boil water and then use that expanding water as it turns into steam to run over some sort of a turbine to get mechanical motion. Now, we've been talking about Rankine cycles. And Rankine cycles have been on the decline in the US because we've been moving away from coal power. But as of 2019, coal power still made up almost a quarter of the energy that we put onto the grid here in the United States. And another Rankine cycle, so another way to get heat to boil water, is in a nuclear reactor. So I remember I've probably told you this before, but I remember being sort of a little bit surprised and maybe even a little bit disappointed when I found out that what a nuclear power plant does is we sort of are harnessing this idea that we can split the atom, right? This enormous accomplishment for human beings. And, we do it because it generates heat and we can use that heat to boil water, right? So it's a steam engine, right? It's just a steam engine that generates heat in sort of the most complicated way that you possibly could, right? So together, right, Rankine, just looking at coal and nuclear, which are sort of the two big types of Rankine cycles that you'd see here in the US, that accounts for about 45% of the power generation that we have, according to this website here, EIA.gov. So when we have a Rankine cycle, we've been talking about sort of this most basic version of a Rankine cycle, where the purpose of the Rankine cycle is to develop power. So we need steam at high pressure going into this turbine, and as it expands, the pressure drops, but as it expands, it's also going over these fan blades, and that causes this shaft to spin. And that spinning shaft gives us mechanical power. Right? Now, all these other components, the condenser, the pump, and the boiler, we sort of string these together just so we can get back to the inlet to the turbine so we can develop more power. Right? And we talked about how to draw these on a TS diagram. So this will be important potentially for the exam tomorrow, where a Rankine cycle, a 4-part Rankine cycle, operates between some low pressure and some high pressure. That's the dashed lines here. And we're going back and forth across the vapor dome from steam, right, down to maybe high quality sort of saturated mixture. And then we condense down to a saturated liquid, right? So we've gone from steam to liquid to increased pressure. And then at this high pressure, this is where we add heat and we boil that water. So now we have high pressure steam and we can go back through that turbine. So knowing how to draw these TS diagrams is important. We remember when we're talking about ideal turbines and pumps, really, if we can make a series of assumptions about the turbine and the pump, we can treat these as isentropic turbines and pumps, where they have this vertical line going between state 1 and state 2s, which is the isentropic outlet of the pump, or of the turbine in this case. And then as we go through that isentropic turbine, the dashed line here goes from 3 to 4s, also a vertical line so that it's isentropic. And then we might use the efficiency, the isentropic efficiency of a turbine or a pump to find the real exit of our turbine, state 2, or the real exit of our pump, state 4. So knowing how to draw these diagrams is an important skill. So we've been talking about how do we characterize different cycles, right? And one of the important questions I think we need to ask is, what's this characterization parameter? And we know the characterization parameter is the energy benefit divided by the energy cost. So when we're talking about heat engines, the energy benefit is power in some respect. In this case, it's going to be the mechanical power that we get from that spinning shaft, the power we develop in the turbine. But because we need to run the pump, that net power is really the turbine power plus the pump power, which is negative. So it's the turbine power minus the magnitude of the pump power. And then the energy cost is that we have to add heat. Now, typically with Rankine cycles, we get that heat by burning coal or by running some kind of a nuclear reaction. So when we're talking about Rankine cycles, the characterization parameter we have for all heat engines is a thermal efficiency, where our desired energy effect is our net power, and we divide that by the heat in, right? Not the net heat. So what we're trying to say is of the input power, how much of that power do we turn into, or the input heat rate, how much of that do we turn into mechanical power that we sort of develop in the turbine and put out onto the grid? We know that the Carnot efficiency is given by T hot minus T cold divided by T hot. Notice that at least one of these temperatures is not a temperature difference, so we would need to use an absolute temperature or Kelvin or Rankine in order to calculate this Carnot efficiency. Now, if we're not doing an ideal Rankine cycle, then what we need to do is look at each individual component. So for the turbine, the pump, and the boiler, this is what we need for the thermal efficiency, right? Because the turbine, the net power is going to be determined by the power in the turbine and the pump, and the heat in happens at the boiler. So the textbook will just give you equations, but I'm always in favor of deriving those equations ourselves from the first law, because then on a test, like the one you're going to write tomorrow, you'll demonstrate to me that you know how to make the different assumptions that simplify this long version of the first law we have for open systems. You're going to simplify that down into an equation that we're maybe more familiar with for heat rate or for power. So you'll assume things like the systems are at steady state. There'll often only be one inlet and one outlet. We'll often assume that kinetic energy can be neglected and that potential energy can be neglected. And then for each component, we'll say that it's adiabatic, we'd say that for a turbine and a pump, or that it's passive, meaning that there's no power, and we'd say that for the boiler. Now, in these cycles, we'll also assume that there's no friction losses or heat losses in between the different components, so that the outlet component, or the outlet state from, say, the turbine is equal to, say, the inlet state from the condenser. When we do this, if we can make the assumptions we're used to making, then for the turbine and the pump, we'll get that W dot is equal to M dot times H in minus H out. And for the condenser and the boiler, we'll get that Q dot is equal to M dot times H out minus H in. You can memorize these if you want. It'll probably just happen to you regardless of whether or not you want it to happen, because you'll do this enough times. But you don't have to memorize any of these things. They all come from the first law. And if you start from the first law, then as you're canceling out different terms, you're demonstrating that you understand the assumptions that we're making to get to these different equations. Now, we expect that the turbine power is positive and that the pump power is negative. We also expect that the boiler heat rate is positive and the condenser heat rate is negative, right? And this comes from this hip to wind convention. So I've talked before that the textbook a little bit kind of drops this convention halfway through the text when it starts to talk about cycles. But for us, I think it's easier. There's fewer things to remember what goes where if you just keep this sign convention and you derive all of these equations from the first law. But when you get to this point, you'll have symbolic solutions that'll depend on delta H in this case, or maybe delta S in some other cases. So you'll have to ask, what's the fluid? And as we move through different cycles, the cycles will be differentiated in part by what the characterization parameter is, and in part by what the fluid is. So if we're talking about a Rankine cycle, we're talking about water typically as the working fluid, although it could be with any working fluid that's moving back and forth across the vapor dome. And in all those cases, so even if you were doing a Rankine cycle with, say, a refrigerant because you were operating at some different temperature, the strategies you would use to find H's and delta H's would be the same. So in particular, the one that I think most people mess up if they're going to make a mistake here is that for the isentropic or ideal pump, we will make the assumption that delta H is equal to the specific volume at either state, because they'll essentially be the same, times delta P. So that only works if the pump is isentropic. But if we do that, we'll get some idea of what the power consumed by that ideal pump would be. Now, in the last class before the review, we did an example problem with a Rankine cycle, a 4-component Rankine cycle that had isentropic efficiencies for the turbine and the pump that were both 85%. So this was not an ideal Rankine cycle. And we found that the thermal efficiency in this case was just over 28%. Right? I think the Carnot efficiency for this case was something like 55%. So we know that it's not fair to compare our actual thermal efficiency to 100%, right? Because we can never get there. But the Carnot efficiency was still 55%, so that shows us that there's room for improvement, right? So today's class is going to be about how we can improve the efficiency in these Rankine cycles, right? So as we see, the thermal efficiency for this Rankine cycle was 28.4%, but if we find the Carnot efficiency, assuming that we're assuming some temperatures for the hot reservoir and the cold reservoir here, but the Carnot efficiency here was on the order of about 55%. So there's definitely room for improvement, right? And if you went into a nuclear power plant, it would not be only this kind of 4-component system. So we'll talk about some strategies that we can employ to improve efficiency. So in particular, as we're improving Rankine efficiency, today we're going to talk about superheat, reheat, and regeneration, right? So why do we want to improve thermal efficiency, right? So this is kind of the questions we should always be asking anytime you're kind of sitting in a lecture. It's kind of like, why do I want to spend my time listening to this for an hour, right? And when we're talking about thermal efficiency, there's really 2 different reasons why improving thermal efficiency is good. Now, the first is a monetary reason, because if we improve thermal efficiency, what that means is that as we're operating our power plant, to get the same power out, we're reducing the amount of coal that we're burning, right? Or maybe we can, we're reducing the amount of uranium that we're consuming in a nuclear power plant, right? So this means that we can save money. Or if we're performing the same heat transfer, however we're generating that heat, if we're burning the same amount of coal or we're running the same nuclear reaction, if we improve our thermal efficiency, that means we get more work out. We get more bang for our buck, right? So when you're talking to your supervisors at work, sometimes it's nice to be able to speak the language of business, right? Because a lot of times as engineers, we're sort of the intermediary between, I think as engineers, we have this social responsibility, right? So we're sort of the stand-in for people that will be using the technologies that we're kind of developing or improving. So it's important for us to have that sort of concern, but we also have to talk to people that are ultimately going to make the decisions. And since there's a profit motive for businesses here in the United States, we want to be able to talk about the economic benefits of these types of improvements as well. Right? But the second is obviously, as citizens of Earth, right? So I like living here on Earth. There's nowhere else I'd rather live, right? So, if we're burning coal to make heat, I think I'd prefer to burn less coal, right? Or less natural gas, right? So if we're trying to make the same amount of power, I would prefer that we add less heat because there's detrimental environmental effects from making this heat transfer, right? So, there's kind of the environmental part, but there's also the economic part. And the nice thing about improving efficiency is that it kind of helps both of these things, right? So, these are the kind of arguments that we can make as engineers when we're advocating for things that improve thermal efficiency. So some of these ideas about how to improve thermal efficiency can come from an equation that's as simple as our Carnot efficiency equation, right? So here with the Carnot efficiency, if we make some simplifications, it's 1 minus T cold over T hot. I would like this number to be as close to 1 as I can, right? And since this is 1 minus something, I want this part of the equation to be as small as it can be. So really, there's two ways to do this, right? You don't have to be a mathematician to see that this part gets smaller if T cold gets smaller or if T hot gets bigger. So when we look at this Carnot efficiency, even though it's a very simplistic model, right? It's this ideal engine that actually can never exist in real life. But if I look at this and I say, well, if I could increase T hot, I'm at least improving the maximum efficiency that I can get, which probably leads to the improvement of real efficiency. Or I can reduce T cold, right? So from this very simple equation, we can see as engineers, here are two potential things that I can try to do to get better performance, right? So how do we increase T hot? So one of the ways that we can do this is we can superheat the fluid, right? So we can boil fluid, right? So we can take this liquid that's at high pressure, add heat until it's a saturated vapor, right? And then we come down here, right? But we could also add some more heat, right? So that when we go through this turbine, the turbine inlet is not a saturated vapor, but a superheated vapor. So if we do this, if we follow the orange line here, what happens is we do pay a higher price, right? We're increasing the amount of heat that we put in the system. But we increase the enthalpy of this saturated vapor more quickly, I think, than when we're increasing the enthalpy of this liquid, right? Because it's already boiled, the liquid, right? So, the temperature kind of runs away as you heat up steam. So if we do this, we're adding heat, but we're also getting more power out, right? So here, we're traveling a longer distance here along our isentropic turbine in this example. So we're getting work out, right? And we know to improve efficiency, right? In this case, because the pump power stays the same. So to improve efficiency, we need the turbine power to be increasing more rapidly than the heat in, right? And we do this, or this does happen when we superheat the fluid, right? So if you superheat, then you get increased thermal efficiency. There's another thing that we can do to increase T hot here, and that's got to do with increasing the pump power that we put in. So if we increase the pressure here, we can even get to a point where our pressure is higher than the critical pressure. Now remember, the critical pressure would be the pressure line that just kisses the top of the vapor dome here, right? So that critical point, remember that critical point is where you can have, it's the highest state where you can have liquid and vapor coexisting at equilibrium. So here, if we go supercritical, right? Supercritical means beyond the critical point. In this case, beyond the critical pressure. So here, P1, right? So this particular constant pressure line never cuts through the vapor dome. So if I do this, then now I'm increasing T hot that goes into the turbine, right? And I'm also getting this longer line. And again, if I have this supercritical cycle, then the power that I'm generated from the turbine increases faster than the heat that I'm putting in, right? And maybe it's a misnomer a little bit to just say the power that's increased from the turbine, because it's really the net power, because over here we have to put in more power in the pump here as well, right? So the net power, which is the pump power plus the turbine power, increases faster than the heat rate going in, and that increases our thermal efficiency. Right? And when we do that, right, and part of the reason for this is that we've talked about this before. Remember, backwork ratios tend to be very low in these Rankine cycles because it's comparatively easy to increase the pressure of a liquid than, some compressible fluid like an ideal gas or steam, right? So if we move to one of these supercritical cycles, that's another way we increase T hot, which is another way that we increase our thermal efficiency. Now, we might look at this, right? And remember our Carnot efficiency was 1 minus T cold over T hot. And, there really is no, why can't we just increase T hot to infinity? Right? And that's because we're limited by certain things inside our system. So in particular, we can't have the temperature going into the turbine be so hot that the turbine melts. Right? So there's some material properties of the turbine. So we need to be friends with materials engineers who are making new steels, right? Or other metals that we use to make turbines. We also need to be friends with chemical engineers because we can only heat up the working fluid as hot as whatever our heat source is. So we need some, whether it's the combustion temperature of the fuel or whatever temperature comes off our nuclear reaction, we need to be able to have, if we think about it as an oven that we're using to heat up this liquid into a vapor, we need to be able to get that temperature very high in order to increase the temperature. So there's at least these two limitations on how hot T hot can be. So now we can also, right, remember our Carnot efficiency was 1 minus T cold over T hot. So another way to improve efficiency here is to reduce T cold. Because if we could reduce T cold all the way down to 0, we'd have 1 minus 0 over who cares what T hot is, because 0 divided by anything is going to be 0. So we can reduce T cold by, so normally in problems we've talked about, this condensation process happens at atmospheric pressure. But if we go through this turbine to some pressure that's below atmospheric pressure, then we would be condensing at some lower temperature, right? So we'd have a colder T cold, right? You see, if we do this, the line for our turbine process again gets longer, which suggests that our net power is increasing, right? Now the line for our pump also gets longer, but again, the power we put in at the pump tends to be relatively low compared to the power that we get out of the turbine. So T cold is often limited by the environment. Because remember, we need to reject heat from T cold. So we need our cold reservoir to be colder than whatever this temperature is that we're trying to condense at. So if we do this, we are increasing the pump power. In this case, in this diagram here, we're adding the same amount of heat, but we're getting more turbine power out. That gives us increased power. And the power increases faster in this case than the heat rate because the heat rate's not changing. So we increase our thermal efficiency. So we see just from looking at this simple equation for Carnot efficiency, there are ways that we can improve efficiency by either increasing T hot or reducing T cold. So those are two different ways that we can kind of, just look at this as from our basic equation and improve thermal efficiency. Right? But as engineers, right, part of our job is to build stuff, right? So, what we've been doing in this class so far, right, is, talking about different processes as Lego blocks, right? So I like to think that our 4-component Rankine cycle is maybe, us just learning how to use these Lego blocks, right? So, I got a 2-year-old and she's kind of playing with these Duplos, right? So, they're big, they're easier to put together, right? But conceptually, when she understands that, she gets how to play with Lego. So as she gets older, she'll be able to sort of, in this Lego movie, right, they talk about becoming a master builder, right? So one of the ways that we can improve efficiency in these Rankine cycles is by moving from this 4-component system to something more complicated, right? So we're going to try to become master builders in thermodynamics class, and that's going to happen by increasing the complexity of our Rankine cycle. So if you go to a coal-fired power plant or a nuclear power plant, there's going to be more than one turbine, one condenser, one pump, and one boiler or steam generator. Right? So when we look at the more complicated version of how we do the analysis for thermal efficiency, we would see that we would take the net power divided by the heat in. Right? And we know that that net power is going to be the turbine power plus the pump power, and heat in is the heat that's added at the boiler. Right? So here, if we think about our characterization parameter, the energy benefit is this net power, right? And the energy cost is the heat in, right? So when I look at this equation, I can increase thermal efficiency if I get more net power out, provided I have the same heat, right? Or if I put less heat in, right? So we're going to talk about reheat cycles today. And even though reheat cycles increase both of these two things, they increase the net power faster than they increase the heat in. So I think of reheat cycles, right, or the modification to do reheat as increasing net power in these cycles. Even though, as we see, they'll increase both net power and heat in. So, sometimes if you're looking at a cycle and you have one turbine, and one turbine is good, well, maybe two turbines would be better. So in this reheat cycle, we have two turbines. We have one turbine at high pressure and one turbine that we're calling a low pressure turbine, which is at some intermediate pressure. So the inlet to this turbine is somewhere above the condenser pressure, but somewhere below the pressure of our boiler, right? So it's going to be below this inlet pressure to the high pressure turbine, but above still this condenser pressure. So if we do this, now we have two turbines. And maybe by adding these two turbines, we could get more power out. But the way that we do that is we want more enthalpy in the fluid before we go into the second turbine, right? Because remember, what the turbine's really doing is reducing the enthalpy of the fluid. That's kind of the cost that we pay. But the benefit we get is that we're generating more power through the turbine. So what happens here is in between these two turbines, we heat the working fluid back up. I mean, we've already got this steam generator, right? We've already got this oven. It's already on. So why don't I send my mass flow rate back through here, even if it's at this intermediate pressure? It's going to take some more heat. The heat's going to go back in, but I kind of already have this hot place. So let's use it again, right? And that's why this is called the reheat cycle, because first we heat the fluid, right? We boil it to get back into this first turbine, but then we reheat it to go into the second turbine. So the question is, does adding this second turbine, right? Is it true that if one turbine is good, two turbines is better, right? So does reheat improve the thermal efficiency? And maybe this is a bit of a spoiler, but we probably wouldn't spend a lecture on this if it didn't work, right? So the conclusion is going to be that doing these reheat cycles does improve thermal efficiency. So what happens when we add this reheat cycle? So what we do first is we take away the one turbine that we had, right? Because we're adding some second turbine. But now our high pressure turbine is going to operate at this intermediate pressure. So we take away our turbine line, if we're drawing our TS diagram, and we add some other pressure line that's in between our low pressure and our high pressure. So I've called this PI because it's some intermediate pressure. Now, as I'm drawing this, if I go through my high pressure turbine, right, it's called the high pressure because the inlet is at the highest pressure in the problem, right? Now I go through this turbine, which I'm drawing here as isentropic, and I stop at this intermediate pressure. But, right, so that gives me some power, right? That's my first power sort of process. But now I'm going to add some more heat, and as I add some more heat after I come out of that first turbine, what happens is I still stay at that intermediate pressure, but I move out here up into the superheated vapor region. So now I go through my second turbine, which is my low pressure turbine, and I generate some more power. But now the inlet of this second turbine is at a higher enthalpy than it would have been if I just went straight through, right? So a normal Rankine cycle is almost like having this high and low pressure turbines without this reheat at the intermediate pressure, right? So when I do this, I'm increasing the amount of work that I'm getting out of my turbines, but I'm also adding more heat because I've got this reheat part, right? Now, this might sound a little bit weird, but if I'm going to forget something in the analysis, it's this second heat part, right? So remember that this is called a reheat cycle or a Rankine reheat cycle. So we're reheating, right? So remember there's two places where we're adding heat in this cycle. So when we do this, we are increasing the amount of heat that we put in, right? And we know that's our energy cost. So we're increasing the cost that we're paying. So this only makes sense if we increase the benefit at a faster rate, right? So what happens is we're also increasing the amount of power that we get out. And at least for today's lecture, you'll have to trust me, but we'll check this out in an example next class. But when we do this, we actually get higher thermal efficiency because we add power at a faster rate than we're adding heat. Another way to think of this is that we're increasing the average temperature of heat addition. And when we do that, we tend, that's like T hot going up in our Carnot equation. So what happens is we're increasing our thermal efficiency, right? So we do these reheat cycles. And in a real power plant, we probably do multiple stages of reheating. And then we'll add in some other strategies we'll talk about next class. But doing this increases our thermal efficiency. So a schematic of a Rankine reheat cycle looks like this, like we saw before. It's still got, it's still got a boiler. It's still got one condenser. It's still got one pump. But we split the turbine into two different turbines, one that operates at higher pressure, one that operates at lower pressure. And in between those two turbines, we added heat. So here, if we look at this, going into the high pressure turbine, we come out of the high pressure turbine. Then we add some heat, right? Because we want to drive up that enthalpy going into the second turbine. Then we go through the second turbine, right? And now it's the same as a normal Rankine cycle where we're trying to get back to that first turbine inlet. So we condense the fluid, we increase the pressure when it's a liquid, and then we add some heat to get it to a high pressure steam. So functionally, it's very similar to the normal Rankine cycle, but we've added a second turbine, and in between the two turbines, we add heat. So what does thermal efficiency look like for a cycle like this? It's still a heat engine. For all heat engines, we're going to have net power divided by heat in. So that equation doesn't change. The thing is that the net power equation changes a little bit here, right? So if I look at my processes where W dot is going to be the term that survives, where the power is most important. So I have the first turbine. I have the second turbine. That's different, right? Because before I only had one turbine. So I have two turbines and one pump. So before, my net work was going to be the turbine power, which is positive, plus the pump power. But now that there's two turbines, it's the power from turbine 1 plus the power from turbine 2 plus the power of the pump. But I know that the power of the pump should be negative if I'm using the first law to derive the equation. Now, if I'm adding heat in, this actually looks the same, except that I'm adding heat at two places. So here, I'm adding heat through the boiler. That's kind of similar to the normal Rankine cycle. But then I also have to add heat in the reheat part, right? It's called reheat. And as silly as it sounds, for me, if I'm doing this quickly, it's this second heat transfer process that I forget about. So remember, there's two turbines in this cycle, but there's also two places where we add heat. So my heat in becomes Q at the boiler the first time and Q at the boiler the second time. So it's like the heat transfer rate at the heating and then the heat transfer rate at the reheating. So if I want a thermal efficiency equation for this particular Rankine cycle, I will have the power from the first turbine plus the power from the second turbine plus the power from the pump. And I'll divide that all by the heat added in the boiler the first time and the heat added in the boiler at the second time. right? And that's true for this particular case where I have one reheat sort of cycle in my Rankine cycle. But if I wanted a more general equation for Rankine cycles with reheat, or really for any Rankine cycle, then my thermal efficiency becomes the sum of all my turbine powers plus the sum of all my pump powers divided by the sum of all the processes where I'm adding heat. So this is kind of a generic equation for a Rankine cycle thermal efficiency. So if you remember this equation, you don't have to remember the particulars for any cycle. Or I can ask you some crazy cycle that you've never seen, but you count up the turbines, you count up the pumps, and then you count up the places where you add heat. And if you can do the first law on all those processes, you can find me the thermal efficiency. So how do we do that? Right? So then we got to look at each individual component and do the first law. But this is pretty much the same as it was for a normal Rankine cycle, except we have more components. So we're going to say we're at steady state. Will typically be one inlet, one outlet. We'll typically neglect kinetic and potential energy. We'll say that a process is either adiabatic or passive, unless we have some other information like heat loss from a turbine or something. In between our components, we will typically say that there's no friction or heat losses, so that the outlet from one component is the inlet for the next. And when we do that, we know that our turbines are going to be m dot times h in minus h out, and they should have positive power. Our pumps are going to be m dot times h out minus h in. They should be negative power. Our boilers, where we're adding heat, is going to be m dot times h out minus h in, and we'd expect those numbers to be positive. And our condensers, if we're trying to find heat transfer rate there, will be m dot times h out minus h in. We expect that to be negative. So here are the equations. These are actually, because the state numbers are here, these are just the equations for the normal 4-component Rankine cycle. But functionally, the first law analysis is not different when you add more components, except that the state numbers might change. So if it's power, m dot times h in minus h out. If it's heat, m dot times out, h out minus h in. And let the hip to win sign convention tell you where it's positive and where it's negative. And you add stuff together. It's a Rankine cycle, so when you ask what's the fluid, it's the same as a basic Rankine cycle, and you're just going to, you're going to use the same processes. Again, I think the trickiest part here is for the pump. If it's an isentropic pump, you'll have to remember that delta H is V times delta P. So I know we got an exam coming up, so I didn't want to take up too much of your time with this lecture. So I'm done for today. But if you have other questions, I'm happy to stick around for a little bit and try to answer them.
I have a question on the quiz.
Sure.
For question 3 and 4, how would you I got stuck on those. How would you start those ones?
So you might have to refresh my memory. Let's start with question 3. So what is the question asking?
It is a real turbine transfers heat into the atmosphere at a rate of 45 kilowatts. The temperature of the turbine is 700 degrees Celsius, and the temperature of the atmosphere is 20 degrees Celsius. What is the rate that the entropy enters the control volume by heat transfer?
Okay, so this is a good one, right? So if we wanted the power, right? So this would be a case, right? Remember how here it says common assumptions? So this would be a case if we were doing a first law analysis. For our power term, we wouldn't be able to cancel out Q dot because here we're told that there's some heat loss, right? So if we were doing a first law analysis, we would actually get that W dot is equal to Q dot plus M dot times H in minus H out, because I think there was still one inlet and one outlet. Then we would have to do a second law analysis. So here, if I pull up an equation for the second law, one second. Right, so if I pull up an equation for the second law, which is somewhere in here. Right, so now if you're doing the equation for the second law, which I think is basically what this question is asking you, you're going to say that it's at steady state. There is some heat transfer here, so you got to think about what's the sign for the heat transfer. It's telling you a couple of different temperatures. So you got to think about which temperature to pick and what units the temperature should be at. So here you don't want to pick the temperature inside your control volume. You want the temperature at the boundary or the temperature outside of your control volume. And then you'll have to find m dot times delta S in your case, right? So you'll be able to fix the state at the inlet and the state at the outlet. So that should tell you delta S. Now, in that problem, was it asking you for a value for sigma dot?
Yeah.
Yeah, so the entropy generation rate. So here, if this was on an exam, it sounds like they're not asking you anything about the power. So you might not have to do the first law analysis. So I would start by writing out the second law, and then I would go through my assumptions, right? So here I would assume that it's at steady state, so this term would go to 0. There's only one heat transfer term, so this summation sign goes away. I'm losing heat in this case from the turbine, I believe. So here, heat in is positive, so heat out is heat out of my system, so that must be negative heat transfer rate. The temperature of the surroundings, so they gave me 2 temperatures. I got to figure out what's the temperature outside of my control volume. I also have to remember that this has to be in either Kelvin or Rankine because it's not a delta T. And then, if it's one inlet, one outlet, I could do conservation of mass and show that m dot in is equal to m dot out if it's one inlet, one outlet, and at steady state. So this is going to be m dot times delta S. So I'd have to fix the states to find S in and S out. So then if I can do that, the only thing I don't know in this equation would be sigma dot. So I think that's what the problem is probably asking me.
Yeah, but I was confused on how to fix the states and find the flow rate of the mass.
Okay, so does it tell you how much power?
No.
Can you read me the question again, please?
A real turbine transfers heat to the atmosphere at a rate of 45 kilowatts. The temperature of the turbine is 700 degrees Celsius, and the temperature of the atmosphere is 20 degrees Celsius. What is the rate that entropy enters the control volume by heat transfer?
Oh, so it's just asking you for this term here. So this is the rate at which entropy enters by heat transfer. So it only wants this term. So it's not asking about entropy generation. It's not asking for m dot delta S. It's only asking for this term.
And I had another question on 4.
Okay, do you mind reading the question to me again?
Saturated liquid water enters an ideal pump at a pressure of 0.1 bar. Pressure at the outlet is 5 bar. What is the outlet temperature of the pump?
So here, does it say it's an isentropic or an ideal pump? Maybe I missed that.
Yeah, it's an ideal pump.
So for an ideal pump, the temperature at the inlet of the pump is equal to the temperature at the outlet of the pump. So this one's a bit of there's a lot of red herrings in here. You might be like, oh, I'm going to try to find the ideal power that the pump consumes, or maybe I do a second law analysis or something. But all you have to know is what's the temperature at the inlet of the pump, because across an ideal pump, we assume that the temperature difference is 0. So if it's a saturated liquid that enters at a given pressure, or I don't know if it even told us the temperature, right? But if it gave us a pressure and told us that it was saturated liquid, then we would find the saturation temperature or the boiling temperature at that given pressure. That would be the temperature at the inlet. And in this case, because it's an ideal pump, the temperature at the inlet is assumed to be equal to the temperature at the outlet.
All right, that's all my questions. Thank you.
Excellent. You're welcome. Any other questions?
Yeah, I just had a question. So yesterday, or not yesterday, but last class asked about accessing quizzes. Now, I don't know if I'm doing something wrong or if I'm like the only one, but I can't figure out how to look at past quiz questions.
Okay, I will try to look into that tonight because I don't exactly know how either. So this is one of those things in my courses where the view for me is different than the view for students. So I'll go through right after class today and see if there's anything that's preventing people from seeing what their quiz responses were. Other than that, I'm sorry that I can't like walk you through it or share my screen as we go through it, because there's no way for me to see what a past answer on a quiz was, because I can't do the quizzes.
Okay, that's all right. I was just wondering because, like, last test, I felt like the multiple choice was a bit more difficult than I expected. And the multiple choice is usually modeled after the quizzes, right?
Yeah, so I think that's sort of the idea, is that they're supposed to be modeled after the quizzes. So I will, like I said, so I'll check that out in the next half an hour or something, and maybe send an email to the class if I can figure it out. And even if I can't figure it out, I'll send an email to the class just sort of saying that I'm not exactly sure how to do it.
Okay, thank you.
Okay?
All right. Thank you.
All right. If there are other questions, I'm happy to field them. And if not, thank you for your time. Oh, so you can view past answers. You click on the quizzes tab, and then you click on the down arrow next to the quiz you want to see. Can you check to see if that works for you, Matt?
Yep.
Thank you, Hannah.
Oh, okay. Oh, wait. Hold on. Sorry. I thought I found it, but... See, for me, whenever I click on that, I only have the option of submissions and, oh, you can look at the individual attempts. Oh, okay. That makes sense. Yep.
Thank you very much, Hannah. I appreciate that, because this is always a mystery to me. So I appreciate your help. I will. So it says select submission. So what I'll do is I'll convert Hannah's comment here into an email and send that out to the class.
Yeah, thank you. Because I was trying to figure out for the longest time and I could never get it.
Awesome. Well, thank you. So again, thank you to Hannah, because I didn't know the answer to that one. So I appreciate it. All right. Well, if that's it, I will see you tomorrow. If you do have questions, let me know. Thanks.